در ادامه سری ویدیوهایی که در مورد روش مونت کارلو، روش زیبای مونت کارلو در المان‌های مختلف محاسباتی مثل انتگرالگیری، مثل ریشه‌یابی، حل معادلات دیفرانسیل معمولی ضبط کردم، امروز میخوام براتون در مورد استفاده از روش مونت کارلو در حل معادلات PDE یا Partial Differential Equation صحبت بکنم. مقدمات تا حدودی شبیه هست به همون موارد قبلی، تولید اعداد تصادفی و از الگوریتم تولید اعداد تصادفی، یکتا، فرکانس تکرار اینها، مواردی که قبلا راجع بهش صحبت کردم، مزایا و معایب روش مونت کارلو که اینجا هم دوباره تا حدودی با نگاه خاص بر معادلات PDE عرض خواهم کرد و اینکه به هر حال ما در این روش از آمار استفاده می‌کنیم و از تئوری آمار و احتمالات بهره می‌بریم برای اینکه بتونیم موارد مختلف رو حل بکنیم. عرض کردم که روش‌های عددی ما دو دسته هستند: دیترمینیستیک مثل روش فایند دیفرنس، فایند والیوم، فایند المنت و استوکاستیک که استوکاستیک ها مثل مونت کارلو اینها در هر بار که شما کدتون رو راه می‌کنید یک جواب متفاوتی تولید می‌کنن. اما دیترمینیستیک ها همیشه یک جواب معینی به شما میدن. پس در مورد روش مونت کارلو با یک روش استوکاستیک صحبت می‌کنم. حالا خود روش مونت کارلو اصولاً روش‌های مختلفی میتونه داشته باشه، ولی اون چیزی که من در این ویدیو معرفی میکنم روش مونت کارلو بر اساس رندوم واک هست. حالا رندوم واک چیه در ادامه عرض خواهم کرد که چی هست. و خود همین روش مونت کارلو بر اساس رندوم واک دو دسته میشه، دو کاتگوری میشه، یکی variable step و یکی fixed step. یعنی من وقتی دارم واک میکنم، راه میرم به شکل رندوم، قدم هایی که برمیدارم اگر قدم ها مقدار ثابتی داشته باشند به اون فیکس استپ میگیم و اگر متفاوت باشن قدم هایی که من برمیدارم وریبل استپ گفته. خود اینها مزایا و معایبی دارن که من در ادامه راجع بهش صحبت خواهم کرد. نکته بعدی هستش که من این در قسمتی که ضبط خواهم کرد به زبان فارسی تقریبا میشه گفت خلاصه و قسمت ابتدایی اصل داستان هست. انشاءالله در ویدیوهایی که به انگلیسی ضبط میکنم شکل کاملتر همین موارد رو عرض خواهم کرد که فقط به زبان فارسی شما آشنا بشید، به عبارتی راه بیفتید و بعد دیگه مراجعه کنید به اون زبان انگلیسی و اونجا کاملتر و توضیحات تکمیلی تری در اونجا هست. نکته بعدی قبل از اینکه شروع کنم خود روش رو بگم، در حقیقت باید دو تا مفهوم رو به شما معرفی کنیم. یکی بحث مارکوف چین هست. مارکوف یک دانشمند روسی بود که یک مفهومی به نام مارکوف پروسس رو ارائه داد و بر اون اساس مارکوف چین یا زنجیره مارکوف رو در بحث آمار و احتمالات مطرح شد که میگوید ما مارکوف چین یک توالی، یک سکونس از اتفاقات هست. حالا این اتفاقات خب در برای کیس ما میشه حل یک معادله، میشه رندوم واک، هر چی میتونه باشه. یک اتفاق که احتمالی این پدیده شما یک پدیده احتمالی است. این ایونت شما اتفاقی است که احتمال رخ داده هر یک از این ایونت هایی که توی این زنجیره هستند وابسته به حالت آماری قبلی خودش هست. یعنی الان اگر من یک چیزی میگم وابسته هستم به قبلی خودم. برای مثال اگر بخوام مثال بزنم، مسابقه معروف هفته که خدا بیامرزدش مجری معروفش رو در اونجا ما یه مسئله داشتیم به نام از کی بپرسم. میگفتیم از یک کسی سوال میشد و اون شخص تعیین کننده بود که نفر بعدی کی باشه. دقیقاً همین افرادی که در حقیقت از هم تعیین میکنن که نفر بعدی کی باشه و این یک زنجیره مارکوف هست که احتمال اینکه به کی بیفته وابسته است به نفر قبلی خودش. یا مثلا تو تست های هوش و اینا داریم دیگه، وقتی چه زنجیره از اعداد به شما میدن که شما باید مثلا 5 تاشو داره، ششمی رو باید تعیین کنید. با تجربه که رقم قبلیش چی بوده شما بعدی رو تعیین میکنید. یا فرض کنید من تو کلاس دارم مثلا یک مبحثی رو درس میدم، میخوام امتحان شفاهی بگیرم. به شکل رندوم از روی لیست دانشجویان نفر اول رو انتخاب میکنم، از اون سوال میکنم و بعد از اون میپرسم که نفر بعدی کی باشه و اون تعیین میکنه نفر بعدی کی هست و بعد از اون میپرسم کی باشه. باز هم یک زنجیره مارکوف رو در حقیقت دارن طی میکنن. این داستان کاربردش در بحث روش مونت کارلو در رندوم واک معنا پیدا میکنه که الان در مورد اون هم توضیح خواهم. بس نکته اولی که عرض کردم کلاسیفیکیشن بود. نکته دوم تعریف مارکوف چین که یک سری از linked events هستش، یعنی اتفاقاتی که لینک شدن، گره خوردن با هم دیگه. بحث سومین مفهومی که عرض خواهم کرد بحث خود رندوم واک هست. حالا فرض کنید همین مارکوف چینی که به شما عرض کردم و همون مثال کلاس درس رو فرض کنید من از یک نفر شروع میکنم به سوال پرسیدن. یه ظرفی هم چیزی هم دارن از اینایی که توش یه سری چیز هست، چپ، راست، جلو، عقب، توش 4 تا گوی هست. هر وقتی از یک شخص سوال کردم دستمو میکنم که اونجا یه گوی در میارم. حالا اگه گفت جلو از نفر جلویش میپرسم، اگه گفت چپ از چپی، راست یکی از این. حالا همین داستان هی ادامه بازیه دیگه، میخوایم یک بازی بکنیم. هی هر دفعه میندازم یه نفر میاد اون مثلا میفته به جلویی، از من نفر جلویی، از جلویی مثلا به چپی، از چپی دوباره ممکنه بره جلو، دوباره برگرده عقب، از اون شخص 2 بار سوال پرسیده بشه. این مسیری که طی میشه در بین دانشجوها، این تراجکتوری، این تریس، این رد پا بهش میگن رندوم واک، حرکتی است، یک جور ترافلینگ هست، جابجایی است بین افراد مختلف توی کلاس که به شکل کاملا رندوم و اون دستمو میکنم تو گوی یکی رو در میارم، اون رندومه دیگه. به این پدیده رندوم واک گفته میشه که خب البته پدیده رندوم واک یک پدیده ارگادیک هست. حالا اینکه ارگادیک در بحث تئوری آمار چی هست اجازه بدید واردش نشم، ولی مثلا ما 2 تا نمونه خیلی معروف از واک، رندوم واک رو اگه بخوام نام ببرم، یکی بحث براونیان موشن. شما در علم فیزیک فکر کنم در فارسی بهش حرکت کاتوره‌ای یک چنین چیزی گفته میشه که حرکت اتفاقی ذرات هوا تو اینجا یا آب تو هر سیال دیگه ای اسمش براونیان موشن. شما یک ذره غبار رو اگر نگاه کنید، خیلی ذره ریز که داره حرکت میکنه، اون تصادفی بودن حرکتش رو میبینید به خاطر اینکه ذرات هوای اطرافش به شکل تصادفی بهش میخورن و این تصادفی با نوسان حرکت میکنه. یا لوی فلایت، L-E-V-Y، لوی فلایت، اینا در انگلیسی کامل هست. اینا همه نمونه‌های پدیده‌های ارگادیکی هستن که جزء رندوم واک محسوب میشن. در واقع ما دنبال این هستیم که براونیان موشن رو شبیه سازی کنیم دیگه. یعنی میخوام ببینم این حرکت ذرات هوایی که اینجا به شکل تصادفی دارن حرکت میکنن مثل همون سوال کننده‌ای که تو کلاس به شکل تصادفی جلو عقب چپ راست میره، من میخوام اینو براونیان موشن رو به شکل عددی شبیه سازی بکنم و چون براونیان موشن یک پدیده تصادفی است مجبور هستم از روش مونت کارلو استفاده بکنم برای اینکه شبیه سازیش بکنم. به خاطر همین هم هست که خب شما میدونید براونیان موشن دیفیوژن جرم و حرارت و مومنتوم مطرح میشه. به خاطر همین هم هستش که این روشی که من میگم توی دیفیوژن هایی که عرض کردم مطرح میشه، یعنی معادلات دیفرانسیل پارشالی که از انتقال حرارت و جرم و مومنتوم به دست میاد. به خاطر همین اکثر معادلاتی که ما با این روش حل میکنیم معادلات الیپتیک یا پارابولیک هستن. معادلات هایپربولیک مثل معادله موج که رفتار موجی دارن، اینها رفتار تصادفی ندارن، اتفاقا جهتدار حرکت میکنن و ممکنه دیسکانتینیتی جوابشون ایجاد بشه، مثل موج ضربه‌ای که تو جهان تراکم پذیر داره. این معادلات رو من جدا باید بررسی کنیم، یک ویدیو دیگه‌ای باید راجع بهش ضبط بکنیم. فعلا من در مورد معادلات الیپتیک و پارابولیک دارم صحبت میکنم. مثلا بزرگش رو الگوریتم روش رو عرض کنم خدمت شما. الگوریتم روش 3 قسمت داره. یکی شما اول باید دیسکریتایز بکنید معادله پارشال دیفرنشیال ایکویشنی که به شما داده شده است. این هر روشی که شما دوست دارید معمولا فایل دیفرنس استفاده می‌کنید دیگه. این قدم اول مخصوص به فیکس استپ مونت کارلو هست. در وریبل استپ شما خوشبختانه این قدم میتونید حذفش بکنید. یعنی قرار هست شما از روش فایل دیفرنس بلد نیستید، فایل دیفرنس چیه؟ می‌خواید مستقیما خود معادله رو حل بکنید. خب این از وریبل استپ که من حالا در ویدیو انگلیسی احتمالاً بیشتر راجع بهش صحبت خواهم کرد، ولی در روش فیکس استپ که من دارم توضیح میدم شما قدم اولتون این هستش که معادله پی دی رو تبدیلش بکنید به یک مجموعه معادلات سیستم اف ایکویشن ها، دستگاه معادلات جبری، مثل کاری که ما تو همه جا می‌کنیم. توی مثلا فاین دیفرنس هم دیسکریتیزیشن یعنی گسسته سازی، شکستن یک معادله پی دی به یک مجموعه‌ای از معادلات جبری. قدم اول است. قدم دوم باید رندوم واک رو شروع بکنید، یعنی از لابلای این نودهایی که تو شبکه هست مثل همون کلاس درس حرکت بکنید و تا جایی که به دیوار برسید، حالا راجبش خواهم گفت. و قدم سوم محاسبه مجهول مسئله هست. این 3 قدم رو با هم دیگه برید. حالا من مزایا معایبش رو هم بهتون عرض بکنم چی هست. خب مزایا معایبش تا حدی شبیه به سایر روش‌های مونت کارلوه. زمان محاسباتی نسبتاً بالا، حالا از خواهم که نسبتاً بالا منظور نسبتاً چی هست. ولی دو تا مطلب الان میخوام خیلی ساده بگم. اگر به شما گفتن که مثلا توی مسئله مجهول مسئله تیه، مثلا دماست فرض کنید، دمای این نقطه از اتاق چند است در این زمان مشخص، من کاری به سایر زمانها ندارم و کاری به سایر نقاط، من دمای اینجا رو توی 1 ثانیه پس از آغاز حرکت، آغاز اون مسئله میخوام. شک نکنید که بهترین انتخاب شما روش مونت کارلوه. یعنی هر وقت شما پوینت خواستن، یه نقطه و یک زمان رو خواستن، از روش مونت کارلوه با کمترین زمان محاسباتی استفاده کنید. ولی در سایر روش‌هایی که ما داریم مثل فاینت دیفرنس یا فاینت والیوم، شما برای رسیدن به یک زمانی باید از زمان‌های پیشی عبور کنید حتما. خب من سایر زمان‌ها رو نیاز ندارم، من اون زمان رو میخوام فقط. چرا باید عبور کنم؟ یک عیب اون روش‌ها این هست. یا برای اینکه بتونم دمای یه نقطه رو پیدا کنم، باید همه نقاط رو همزمان با هم طی یک دستگاه معادله‌ای حل بکنم که نه تنها اون نقطه، بقیه نقاط هم به دست بیان، با هم همگرا میشن. ولی در روش مونت کارلو شما یه نقطه رو فقط به دست میارید. حالا اگر بخواید همه نقاط رو به دست بیارید، اون پروسه رو باید برای همه نقاط تکرار کنید یا برای همه زمان‌ها تکرار. به خاطر همین اگر به شما بگم کلا همه جا نقطه زمان چقدره و در کلی زمان‌ها روش مونت کارلو هر زمان خواهد، چون برای هر نقطه و هر زمان باید این کار تکرار کنید. ولی اگر به شما بگم فقط در یه زمان و بدون توجه به سایر زمان‌ها و در یک مکان بدون توجه به سایر مکان‌ها دما رو من بده، بهترین انتخاب روش مونت کارلوست که البته همین باعث میشه تو روش‌های مثل روش اینورسی ترانسفر، انتقال حرکت معکوس که یک مسئله ایمپولس هم هست، استفاده از روش مونت کارلو معنادارتر باشه و راحت‌تر باشه. نکته بعدی هستش که روش مونت کارلو مزیت دیگه‌اش اینه که به بعد مسئله وابسته نیست. یعنی چندان اگه مسئله یه بعدی رو شما حل کنید، دو بعدی هم همونه تقریبا، زیاد فرقی نمی‌کنه. سه بعدی هم همونه. شما درگیر با سختی‌های ناشی از بعد مسئله نمیشید. کدنویسیش خیلی ساده است. مزیت سوم. چه برسه حالا که به بعد و اینا وابسته نیست. ولی کدنویسی بسیار خواهید چقدر ساده ما میتونیم مسئله رو حل بکنیم، مسئله پی دی رو حل بکنیم. کدنویسی ساده، مموری کمی کامپیوتر نیاز دارید. اینها مزیتش هست. ولی خب برای عرض کردم اگر یه مقدار همه نقاط رو بخواید ممکنه زمان محاسباتی زیاد بشه. و مزیت چهارم یا نمیدونم پنجم این هستش که کاملا سیستم مناسب، روش مونت کارلو مناسبه برای استفاده رو سیستم‌های پردازش موازی است، چون محاسباتش تفکیک پذیره. شما میتونید همزمان چند تا کار رو با هم دیگه انجام بدید. قرار نیست، وابسته نیست، محاسباتش سری نیست، موازیه. مثلا همون کلاس درسی که من امتحان شفاهی میگیرم، میتونم از یکی از همکارانم دعوت کنم بیان تو کلاس همزمان دوتایی با هم امتحان شفاهی بگیریم. مثلا کاری ندارم با اون شخص که نفر دیگه چجوری همزمان با هم این پروسه رو طی بکنیم. بخاطر این برای سیستم پروسسینگ هم خیلی مناسب است. خب من شروع کنم برای یک مسئله دو بعدی عرضم حضور شما که این رو کاملا بیان کنم و یاد بگیرید که برای چگونه باید مثلا فقط مواردی رو که نخواهم گفت رو در امتحان میگم که در انگلیسی ان شاءالله ادامه خواهم داد. معادله‌ای که با هم دیگه بررسی خواهیم کرد به عنوان مثال معادله لاپلاس هست. فعلا سمت دوم تساوی رو صفر نظر بگیرید. توی ویدیو انگلیسی من در مورد اینکه اگه معادله همگن نبود سمت دومش صفر نبود چه کار باید بکنیم هم توضیح خواهم داد. مساوی سه دو بعدی سه بعدی یا این همین هست، خودتون دیگه این همین کاری که من میکنم تو سه بعد خودتون انجام خواهید داد. در روش مونت کارلو قدم اول روش این هستش که شما بیایید معادله دیفرانسیلتون رو بشکنید به یک معادله جبری. این قدم فقط در روش فیکس استپ وجود داره. در قدم وریبل استپ شما نیاز نیست این کارو بکنید. اون توضیحاتش من باز در قسمت انگلیسی خواهم داد. ولی این قدم یکی که اینجا می‌بینید اینه که این معادله رو به کمک فاینت دیفرنس برای مثال من میشکنمش به یک معادله جبری شبکه باید انتخاب بکنم که ابعاد این شبکه فیکسته. به خاطر اینکه میگیم فیکس استپ. آی جی نود وسط، آی به علاوه 1 و جی سمت راست، آی منهای 1 و جی سمت چپ، آی جی منهای 1 پایین، آی جی به علاوه 1 بالا. دلتا ایکس طول شبکه در راستای ایکس و دلتا وای که لزوما هم برابر نیستن. به کمک فاینت دیفرنس شما راندوی تی به راند x2 رو میتونید اینجوری بنویسید. حالا که من زیاد وارد این معادله نمیشم، خیلی معروفه دیگه.
و این همین روندوی تی به روند وای 2 رو هم میتونید بنویسید. این آی به علاوه 1 و جی منهای 2 برابر آی و جی به علاوه آی منهای 1 و جی. رو آی تغییر میکنه چون مشتق به ایکسه. وای هم این همین فقط جی به علاوه 1 و جی منهای 1. ضرایب هم 1 منفی 2 1 مخرج دلتا وای به توان 2 خواهد شد در اون حالت. این دو تا رو جاگذاری میکنید داخل اون معادله. همیشه در روش مونت کارلو ما تی آی جی رو میکشیم یه طرف، نوده های همسایه رو هول میدیم اون طرف به طوری که ضریب تی آی جی هم 1 باشه. یعنی اون هر چی اونجا بود طرف فاکتور گیری میکنیم، تقسیم میکنیم طرفین رو به اون که ضریب 1 بشه. پس میشه تی آی جی مساوی پی ایکس پلاس ضریب تی آی به علاوه 1 و جی. آی به علاوه یعنی ایکس پلاس پی آی منهای 1 و جی میشه ضریبش میشه پی ایکس ماینس و بالایی میشه پی وای پلاس، پایینی میشه وای ماینس. این فرمت، این فریم ورکی است که ما در روش مونت کارلو نیاز داریم تا ما رندوم واک رو روش آغاز بکنیم در قدم بعدی. ضرایب حالا من نوشتم اینجا مثلا پی ایکس پلاس تا پی ایکس ماینس یکی هستند و 1 بر دلتا ایکس رو تقسیم بر 2 برابر 1 بر دلتا ایکس رو علاوه 1 بر دلتا وای 2 که میتونید به صورت مخرج دلتا ایکس دلتا وای ضرب بکنید، میشه دلتا وای به دلتا ایکس تقسیم بر 2 برابر دلتا وای به دلتا ایکس علاوه دلتا ایکس به دلتا وای. خب این همین پی وای پلاس این نکته‌ای نداره واقعا، یعنی فقط این دو تا رو که هیچ ننوشتم در روندوی تی روند وای 2 و اینو بذارید اینجا ببرید یه طرف همه رو تی آی جی یه طرف بقیه اون طرف فاکتور گیری تقسیم میشه. خیلی ساده است. پی وای پلاس و پی وای ماینس هم برابرن، میشه دلتا ایکس به دلتا وای تقسیم بر 2 برابر دلتا وای به دلتا ایکس علاوه دلتا ایکس به دلتا وای که اگر دلتا ایکس و دلتا وای برابر باشد، یعنی ابعاد شبکه‌تون یکسان باشه در دو جهت، در اون صورت هر جفت اینا ساده میشن به 1/4. این داره به شما میگه که دمای نود وسط پس 1/4 بالایی 1/4 پایینی 1/4 که میشه 1/4 جمع اطراف. انگاری که دارید متوسط گیری جبری میکنید در حالتی که ابعاد شبکه‌ای باشه. در روش فاین دیفرنس این معروفه دیگه، میگیم که در روش فاین دیفرنس در معادله لاپلاس دمای وسط 1/4 نودهای اطرافش است یا میانگین نودهای اطرافش است. دقت کنید در روش مونت کارلو ما با میانگین اصلا کار نداریم. در برای ما این 1/4 یا بهتر بگم این ضرایب پی ایکس پلاس و ایکس ماینس و اینا احتمالند. احتمال اینکه یک رندوم واک، یک جسمی که به شکل تصادفی حرکت میکنه از نود وسطی بره به بالایی بره به چپی راست، این ضرایب تعیین کننده احتمال حرکت رندوم واک شما از نود وسط به اطرافن. مثلا اگر پی ایکس پلاس 0 باشه یعنی اینکه احتمال اینکه این رندوم واک من که اینجاست بره به ایکس پلاس به نود بغل 0، این ممکن نیست بره به نود بغل. اگر 1 باشه بقیه 0 100% میره به نود بغل. هر چقدر ضریب بزرگتر باشه احتمال اینکه این جسمی که داره به شکل تصادفی حرکت میکنه بره به اون نودی که ضریبش بیشتر احتمالش بیشتر. مثلا و نکته خاص دیگه نیست. و البته وقتی من میگم احتمال یعنی باید قوانین احتمال رو ارضا بکنن. اینا احتمال همیشه یک چیزی بین 0 تا 1 نمیشه احتمال 2 باشه. این ضرایب هم همیشه بین 0 تا 1 هستن، همونجوری که اصلا معلومه. تو این کیس خاص معلومه، تو بقیه حالات هم همین گونه است. خب این همیشه از چون دلتا وای به دلتا ایکس دلتا وای به علاوه یه چیز مثبت شد. اولا اینکه مثبتن همیشه، دوما از 1 هم کوچکترن. این 1 دو اینکه باید مجموع این احتمالات 1 بشه. یعنی اینکه احتمال اینکه بره چپ راست بالا پایین جمع اینا باید 1 بشه که هست اتفاقا. چک کنید پایین این الان این پی ایکس پلاس و پی ایکس ماینس دو به این ضرب کنید چون با هم برابرن. یه دو هم به پایین ضرب کنید به هم جمع کنید. جمعش 1 خواهد شد. این از دیدگاه آماری دارای معناست برای ما. حالا توی فاینیت دیفرنس فاینیت والیومی که این ضرایب باید مثبت باشن یه معنای دیگه پیدا می‌کنه. من نمی‌خوام در مورد اون صحبت بکنم. و حالت بعدی هم زمانی است که معادله دیفرانسیلی که به شما داده شده ضریب داشته باشه. اینجا دقت کنید ضریب شما نباید تابع تی باشه، تابع مجموع غیر خطی میشه. حل معادلات غیر خطی براش مونت کارلو خیلی دشوار است. فعلا فقط تابع ایکس و وای هست. وریبل کوفیشنت معادله اصطلاحاً. دیگه لاپلاس نیست، یه جوری شکل لاپلاس دیگه. می‌خوام ببینید که اونم میشه به راحتی حل کرد. و کاری که باید خواهید کرد اینه که دوباره همین روندوی تی روند ایکس 2 و روندوی تی روند وای رو جاگذاری کنید اونجا. فقط این دفعه ضریب ای وارد میشه. حالا برای سادگی جوابی که من نوشتم برای حالتی است که دلتا ایکس با دلتا وای برابر باشه. اگه نبودم شما خب معادلاتتون یکم بزرگ میشه. اگر برابر باشه اینو جاگذاری کنید اونجا. پایلیز پی ایکس پلاس و پی ایکس ماینس میشه ای آی و جی تقسیم بر 2 برابر یک علاوه ای آی جی یعنی مقدار اون ضریب ای که تابع ایکس و آی در اون نود وسط در اون آی و جی که رندوم واک شما اونجا حضور داره فعلا. باز ببینید اگه ای آی جی 1 بذارم میشه معادله لاپلاس، اگه 1 بذارید دوباره میشه 1/4 و 1/4. خب این از قدم اول برداشتم تو روش فیکس رسه، اگه وریبل استیت باشه نیازی نیست این قدم رو انجام بدید. شما قدم دوم میخوام رندوم واک رو اجرا بکنم. رندوم واک بدین گونه اجرا میشه که شما همون داستان دانشجوها و کیسه و یه چیزی بردارم ببینم چپ راست بالا پایین کدوم وری حرکت کنم، یه نقطه آغازین داره. یعنی باید به شما بگید ما دمای کجا رو میخوایم، میگه فلان نقطه، میشه اون نقطه شروع رندوم واک. از اونجا یه کیسه هم داریم دست میکنیم، یه بازی دیگه کیسه دست میکنیم توش، اگه در اومد چپ اون میره چپ، راست رو همینجوری 2 بعدی حالا دارم، تو 3 بعدی میشه لغت چپ راست جلو عقب بالا پایین. حالا من 2 بعدی دارم میگم مثلا 4 تا. پس حالا اینکه کدوم جهتی بریم رو کاملا تصادفی باید انتخاب کنیم. پس نیازمند تولید اعداد تصادفی هستیم. generate random numbers. یه سری اعداد تصادفی تولید میکنیم. حالا قاعده بازی ما این هستش که از نود آی و جی که دمای اونجا رو میخوایم شروع میکنیم. این رندوم واک رو به کمک اون تولید اعداد تصادفی چپ راست جلو عقب میریم تا جایی که برسیم به یک دیوار. وقتی رسیدیم به دیوار با دمای مشخص تموم میشه این پروسه رندوم واک ما، ترمینیت قطع میشه. ممکنه 100 تا قدم برسیم اونجا، ممکنه 10 تا برسیم، ممکنه تو اولین قدم برسیم، بسته به اینکه دیوار کجاست و ما کجا هست، شروع حرکت کجاست. در اون صورت دمای دیوار رو در انتهای حرکت ذخیره‌اش میکنیم. این میشه یه رندوم واکی که از یه جایی شروع شده به یه دیواری با دمایی رسیده، ما اون دمای دیوار رو ذخیره کردیم. دوباره این پروسه رو شروع میکنیم از همون نقطه با یه رندوم واک دیگه، چون تصادفی لزوما همین مسیر رو طی نمیکنه، میرسه به یه دیوار دیگه و دوباره دمای اون دیوار رو ذخیره میکنیم. همین کار رو انقدر ادامه میدیم که تعداد رندوم واک هایی که انجام میشه از دیدگاه آماری معنادار باشه. مثلا 100 بار، 200 بار، 300 بار، نمیدونم 2-3 بار به جواب نمیرسه. اگر 1,000,000 بار شما از یه نقطه شروع کنید، تصادفی حرکت کنید، برسید به یک دیوار و دمای دیوار رو ذخیره کنید، این 1,000,000 باری که n بار، حالا من بهش میگم n بزرگ، n باری که این کار انجام دادید n تا هم دمای دیوار رو ذخیره کردید. اون دمای دیوار رو با هم جمع کنید، تقسیم بر تعداد n بکنید، این میشه دمای نقطه. به همین سادگی. شاید هم 3-4 خط کد بیشتر نباشه. چند نکته در اینجا هست. اولا اینکه خب من اون دیوار باید چه دیواری باشه؟ هر دیواری میتونه باشه؟ نه، باید دیواری باشه که حتما دما روش مشخص باشه یا دما توش وجود داشته باشه. نوع 1 یا نوع 3، ریشته یا روبین باید باشه. در مورد سایر انواع شروط مرزی من بگم اگه مثلا دیواری باشه که مشتق است یه چیزی روش مشخصه، اون موقع رندوم واک قطع نمیشه، میره اونجا دوباره ریفلکت میشه، ادامه پیدا میکنه پروسه و بالاخره این پروسه تا جای ادامه پیدا میکنه که برسه به یک دیواری که دما توش مشخصه. نکته بعدی اینه که اصلا ممکنه من به دیوار نرسم، یعنی اینجوری داخل دور خودم بچرخم، پاسخ نست. چه زمان ممکنه به دیوار نرسم؟ زمانی که این پروسه تصادفی که من دارم طی می‌کنم ارگادیک نباشه. باید در مورد ارگادیک من چند دقیقه توضیح بدم. چون پروسه ما ارگادیک هست، حتما بلا شک شما به یک نقطه دیوار خواهید رسید بالاخره. یا اعداد تصادفی من یکتا نباشن، کافی نباشه، تکراری بشن از یه مدت بعد. خب این فرض ما اینه که اینجوری نمیشه. خب پس قاعده بازی رو الگوریتم یاد گرفتید به همین سادگی، یعنی هیچ دیگه واقعا خارج از این نیست. البته دارم ساده‌ترین کیس رو میگم. حالا چیکار می‌کنید؟ شما میاد فرض کنید که این ذرات یکی نیستن. مثلا حالا فرض کنید یکی هم مثلا برای سادگی 25 سال شما دستتون رو می‌کنید تو اونجا یه عدد تصادفی کامپیوتر تولید می‌کنه مثلا. اگه بین 0 تا 25 سالم شد مثلا میگید برو به راست. اگه بین 25 سال تا نیم شد برو به چپ. از نیم تا 75 سال برو بالا. بیا من خب شانسی گفتم اینا رو میتونید بررسی کنید. اما اگر این ضرایب یکی نبودند، این نکته رو دقت بکنید. ما این اعداد تصادفی ما هستن که از 0 تا 1 هستن، اونجوری که می‌بینید. من بزرگترین بدون اینکه از کلیت مسئله کم بشه فرض کردم بزرگترین ضریب بین این 4 تا پی ایکس پلاس باشه. همیشه بزرگترین ضریب رو اول قرار بدید. و بعد کوچکتر تا همونجوری شکل می‌گیره، مثلا هر چند میل جلو کوچیک‌تر شده. اگر عدد تصادفی مثلا این 14 مثلا از قرار 25 صدم باشه حالتی که یکی هم مثلا ذرای جوریه که مثلا این شده 14 شماتیکه ها، اصلا خیلی جدی نگیرید. 4 تا 14 شد، باید برن چون ایکس پلاسه، باید برن به نود آی بله. احتمال اینکه برن به نود سمت راست بیشتره چون ضریبش بزرگتره. اگه بین پی ایکس پلاس تا پی ایکس پلاس علاوه وای پلاس شد، باید برن تو نود بالایی وای پلاس. اگه بین پی ایکس پلاس علاوه پی وای پلاس تا پی ایکس پلاس علاوه پی وای پلاس علاوه ایکس ماینس شد، باید برن به نود چپی. ولی تو آخری افتاد باید برن نود پایین. دو تا نکته، این آخری که یکیه مجموع این چارت هاست چون مجموع ذرای یک هست، اون دیگه یکه. نکته دومی که این سومی اینجوری که اینجا میبینید مجموع این سه تا هست، چون مجموع چارت ها میشه یک، در حقیقت مجموع این سه تا میشه یک منهای این چهارمی. پس دیگه قرار نیست هر دفعه این سه تا رو هم جمع بکنیم، میشه یک منهای چهارمی. تعداد عملیات کمتری فقط خواهد داشت. و نکته بعدی هم این هست که شما اصولا فقط 3 تا مقایسه نیاز دارید. چهارمی دیگه نیاز نیست چون میفته معلومه دیگه این 3 تا نباشه. یعنی در بدترین حالت شما فقط 3 تا مقایسه نیاز خواهید داشت که مثلا در حقیقت بیشترین قسمتی که زمان محاسباتی کد شما خواهد داشت همین قسمت کامپریزن ها هست، مقایسه ها هست. چون هر دفعه باید تست کنید ببینید کدومه. خب یه بخش تعداد متوازن تا حدی که میتونید با تعداد این if statement ها رو در داخل کدتون کمش بکنید. و نکته بعدی هم این هستش که خب شما تو اینجا باید این بازه هایی که اینجا چیدید رو نزولی بچینید. مثلا اگه 1/4 بود مثل مثالی که عرض کردم خب فرقی نمیکنه. ولی اگه مثلا 1/14 بود به شکل مثال عرض میکنم، یکی مثلا بعدش 3 بود، مثلا 2 اینجوری بود، در اون صورت شما همیشه بزرگتر به کوچکتر باید بچینید. چرا؟ میتونید یکم استاپ کنید، فیلمو پاس کنید، فکر کنید، ببینید میتونید دلیلش رو بگید که چرا باید این کارو بکنید. ولی پاسخ این هستش که مترجم می‌کنه تعداد مقایسه ها رو حداقل بکنید. یعنی اگر بازه اولی که اولین مقایسه توش انجام میشه بزرگترین بازه باشه، خب احتمال اینکه شما دیگه نیازمند به مقایسه بعدی نباشید بیشتره دیگه. یعنی که شما تعداد اون مقایسه هایی که در کدتون انجام میشه به کمترین مقدار ممکن میرسه. و نکته بعدی حالا پس از اینکه این انتها رو به دست آوردن repeat random walk n times و کی آیدی در مای اون نقطه آغازینی که در ابتدای حرکت بود تو یک انوم n بار من حرکت کردم به n تا دیوار رسیدم. مثلا در این مثال معروف کبیتی که اینجا هست 3 تا دیوار داریم که 3 طرفش صفر اما بالایی یکه. من نقطه مثلا اینجا رو میخوام شروع میکنم، یه بار تصادفی حرکت میکنم میرسم به 1، بار اول 1، دومی هم میرسم به 1، 2 تا 1، سومی میرسم به این دیوار 0، 2 تا 1 با 0. مثلا شروع میکنم میرسم به 300 بار 400 بار اینو میرم و اون دماهای دیواری که بهش اصابت کردم رو جمع میکنم، تقسیم بر تعداد میانگین اون دمای دیوارها رو به دست میارم. این به خاطر این هستش که ما در مسائلی که پارابولیک هستند یا الیپتیک هستن دمای یک نقطه در داخل رو به کمک دماهای اطرافش به دست میاریم. به خاطر وجود همون پدیده براونیان موشن یا دیفیوژنی که تو مسئله وجود داره از همون الهام گرفته شده روش. این به همین سادگی 2 خط کده. شما این دیسکریتیزیشن رو که رو کاغذ انجام میدید یا اصلا اگر از روش وریبل استپ استفاده کنید نیاز به این هم نداره. قسمت دوم یه حلقه شروع خواهید کرد برای اون نقطه‌ای که مد نظرتون هست. یه عدد تصادفی تولید میکنید، میره بعد چپ راست مقایسه انجام میدید، چپ راست بالا پایین میره، دوباره تصادفی چپ راست تا زمانی که رسید به دیوار تمام یه عدد رو ذخیره میکنید. همین کار رو 100 بار 200 بار انجام میدید، تقسیم نقطه 3 خط کد نشه. حالا اگر نود دیگری رو خواستید یه نود دیگر هم همین کار رو دوباره برید یه حلقه هم واسه نقاط بذارید برای هر کدوم از نقطه این پروسه طی بشه. این مواردی بود که من عرض کردم. ولی یک سری نکات هم رو دیگه الان در ویدیو فارسی عرض نخواهم کرد. اینها رو بعد نیست با هم مرور بکنیم که انشالله در ویدیو انگلیسی اینها رو با هم دیگه ادامه خواهیم داد. یک مثال هم من خواهم داد از کیس یه بودی. این بازی رو با هم دیگه در حالت یه بودی انجام میدیم ببینید چقدر ساده و چقدر دقیق میشه به جواب رسید. عرضم بوده مثلا یه تابع که سمت دوم تساوی صفر نباشه، در اون صورت سورسن داخل مسئله باشه، این معادله لاپلاس اون میشه معادله پواسون. عرض هم کرده چطوری میشه معادله پواسون رو در وقتی که جمله سورسم تو مسئله وجود داشته باشه مثلا رو حل کرد. اگر شروط مرزیمون دلیشته نباشه لزوما دما ثابت، مثلا نادیاباتیک باشه یا مشتق باشه یا یه ترکیبی از مشتق و خود تابع باشه، عرض هم کرد چیکار خواهید کرد؟ و اون نکتهش اینه که فقط اونجا دیگه وقتی رسید به دیواری که مشتق از داره دیگه این رندوم واک قطع نمیشه، ادامه پیدا میکنه، ولی اون تیکه با یه فرمول جدیدی ادامه پیدا میکنه. بعد شروط مرزی دیوارهای منحنی رو خواهم گفت، وریبل استپ متد رو اینجا معرفی خواهم کرد به شما. مسائل تابعیت زمان داشته باشن رو معرفی خواهم، یعنی جمله راند تی اینجا باشه، تی دوم که گفتم زمان هست. در اون صورت خواهید مثلا میتونید فکر کنید ببینید این چیزی که من گفتم چجوری میشه به مسائلی تابعیت با زمان درشون هست اکستند کرد، گسترش داره. میتونید فکر کنید ببینید چجوری میشه این کار کرد. و ارزم حضور نیست این نکات دیگری که انشاءالله در قسمت‌های بعدی با هم دیگه دنبال خواهیم کرد.
Today I'm going to speak about the Monte Carlo method for this numerical solution of partial differential equations. I've already recorded some videos about the Monte Carlo method for the solution of ordinary differential equations, or in root finding applications, or computing integrals. But in this series of videos, I'm going to discuss the Monte Carlo method and development of this stochastic statistical method for the solution of partial differential equations. Okay, let's start. The Monte Carlo method for the solution of partial differential equations can be classified in two categories. The first one is called the fixed step method, and the other one is the variable step, or the floating step method. It's obvious from the title that in the first item, the step size during the Monte Carlo method is fixed, but here the step size can be variable. So the second method is appropriate for the solution of problems with curved boundaries. Okay, the main concept or the central concept of the fixed step method is to convert the partial differential equation into a system of equations similar to what we do in discretizations in finite difference algorithms or finite element method. So we have to discretize a partial differential equation into a system of equations like this. Here it is the unknown function, for example, temperature, electrical potential, or anything else. Our unknown function at the grid point I and j are counters of grid numbers. It equals the summation of t at neighboring cells and shows the neighboring points in space. P sub n is the coefficients which connect the neighboring point to the central point, shown by t sub ij. In Monte Carlo framework, we call these coefficients probabilities. It means that if the probability of connection of a point ij and point I plus 1j is 0, it means that there is no connection between them. So the probability of traveling from the central point to the next neighboring point is 0. So based on the statistical fundamental rules, the probabilities should be positive numbers or non-negative numbers, and also sum of all probabilities should be equal to 1, equals 1. So this is the framework of Monte Carlo method when we use the fixed step scheme. So here you have to first discretize the equation into a system of algebraic equations. So you need a discretization algorithm first, for example, find difference. But in this section, there is no need to discretization process, and you can directly solve the partial differential equation. Or specifically when there is curved boundaries in your problem. Okay, this is the classification of Monte Carlo method. The other concept here is the Markov chain. Markov chain is a very well-known concept in stochastic mechanics or in statistics. It says that Markov chain is a stochastic process or sequence of events
Events in our case, I mean the solution of partial differential equation, means is the traveling from one point to the other. This is our event here. But generally speaking, event can be any other statistical event. It's a stochastic process or sequence of events in which the probability of each sample or each event is dependent on the statistical state of the previous event. So when I want to compute the probability of event at a specific step, I have to compute it based on the previous step. For example, consider that I'm teaching for fluid mechanics in a class, and I'm going to ask questions from students in the class. The first student is chosen based on a random selection from the list, and I ask my first question from the random student from the list. Okay. The next question is determined by the first student. For example, after I ask my questions, I ask him or her, who is the next guy? And he or she says that ask your next question from his friend, for example, or her friend. And this is an example of a Markov chain. So, because the next student is determined by the statistical state of the previous student. Okay, so we have a sequence of events, cos of 0, cos of 1, to cos of j. J starts from 1 to infinity. So the Markov chain is a chain of linked events. Or we have well-known questions in IQ tests. I give you a sequence of numbers, and I want you to guess the next number in the list. So you have to find a relation between the previous numbers and construct the solution based on the relations between the previous steps. This is again somehow like an example of the Markov chain process. The next concept in stochastic process or in Monte Carlo solutions is the random walk, RW, random walk. And random walk is a Markov chain type, a Markov chain type path. So it is a path trajectory of something, because we say random walk. When someone starts to walk, you can specify the trajectory of the random walk. So this is a Markov chain type path that consists of random steps. For example, again, let's go back to my example of students in class. These points here are students. I start asking questions from this guy here, and he or she says that the next student is this one. So this is the path from the first student to the next one. And continue this random process. The next student, this one, and this is a random traveling from the first student to the last one, randomly. So we have a Markov chain events, which is the label of students or the name of students. And the path of this Markov chain traveling or Markov chain journey from the first one to the last one is called the random walk process. Two well-known examples of the random walk are the Levy flight, and the Brownian motion in diffusion of heat, diffusion of momentum, or diffusion of mass. So I don't want to speak about these processes because they are somehow physical, but a random motion of particles in a fluid is called the Brownian motion. For example, consider a dust particle, small dust particle moving in there. If you focus on it, you will see that the motion of dust particle is somehow random because of random collision of air particles adjacent to that dust particle. The motion of the dust particle is also random. So you can see the Brownian motion here, but if you inject, for example, a drop of ink into the water, you can see the Brownian motion or the random motion of water particles. So we are trying to mimic the Brownian motion, but the Brownian motion is about the particles. So particles are very, very small part of a substance. So, but here the distance between 2 points in space is not infinitesimal, is not differential. So when the distance between 2 points in space goes to 0, this random walk process goes to the Brownian motion. And also the other point here is that, you know, the Brownian motion is the dominant process in diffusion problems, diffusion of heat, mass, or momentum. And again, you know that the partial differential equations resulting from the diffusion of different process is parabolic or elliptic. So this kind of solution, Monte Carlo solution for partial differential equation is can be used for the solution of parabolic and elliptic equations. There are some corrections or modifications for hyperbolic equations, which contain some sharp discontinuities, such as the Berger's equation or shock waves. But here in this video, I'm speaking about the Monte Carlo solution of the parabolic or elliptic equations, partial differential equations, based on the random walk concept. The other point here is the ergodic process. You know that the Brownian motion, based on the concept ergodic process in statistics, the Brownian motion and also the Levy flight are both ergodic processes. And here, the random walk process also should be an ergodic process. Okay, this is the classification of Monte Carlo methods for the solution of parabolic and elliptic equations. This is the Markov chain concept, and this one is the random walk concept. Based on these concepts, I can introduce the algorithm of the Monte Carlo method for the solution of partial differential equations. But before that, let's speak about the advantages and disadvantages of the Monte Carlo method. Is used to compute the value of the unknown function at each point in space or position and time, independent of other positions and time. This is the main advantages of the Monte Carlo method for the solution of partial differential equation. You know, when you discretize the partial differential equation, using finite element method, finite volume method, or any other numerical method, you have many unknown functions in grid space, in grid points in space, and you have to solve a set of equations or a system of algebraic equations simultaneously. So, if you want to compute the temperature at a point, at a particular point in space, you have to also compute the temperature of other points, and these system of equations simultaneously converge to the solution. But consider that you just want to compute the temperature at a specific point in space. You don't need to compute the temperature of other points, or even at other times. I am planning to just compute the temperature at a specific point and a specific time. In this case, the best choice for you is the Monte Carlo method. So, computing the value of the unknown function at each x vector means the position vector, and time independent of other positions and times. This strategy is well appropriate for inverse heat transfer problems. So if you are trying to solve an inverse ill-post, of course, heat transfer, the numerical, the Monte Carlo is a good choice for you as your numerical method. And no need to the system of equations. This is called the point value. So if you want to compute the point value of the unknown function, the best numerical method is the Monte Carlo method. And the other advantage of the Monte Carlo method is that no sensitivity to dimension. It means that you can easily extend your code, your numerical code, to three-dimensional geometries, and you're from one-dimensional to two-dimensional. But it's somehow difficult in other numerical methods to develop a one-dimensional code for two-dimensional cases or three-dimensional cases. But no sensitivity to dimensional geometry. The other advantage is low memory of a computer, and also even time. If you want to compute the temperature at the point, you can easily use the Monte Carlo method with very low computational time. But if you want to compute the total time and total points in space, it's maybe expensive. The Monte Carlo method may be expensive. But if you're targeting a point in space at a specific time, the best choice with the lowest computational cost is the Monte Carlo method. And also, similar to other Monte Carlo algorithms, the MC method is well appropriate for parallel processing systems, because the computations can be done separately, and you can separate computations, and you can simultaneously perform the random walk starting from points in space using different cores, and tremendously and remarkably reduce the computational cost by using the parallel processing. For example, here in our example of students in class, I can ask my colleague to come to the class, and simultaneously we can ask questions from different students in class, 3 questions at a time. So the main advantage of the Monte Carlo method is its flexibility for parallel processing programming. Here I'm going to describe the process or the algorithm of the Monte Carlo method for the solution of partial differential equation for a two-dimensional, well-known partial differential equation, the Laplace equation. As you see here, any Monte Carlo method for the solution of partial differential equation consists of 3 steps: step 1, step 2, and step 3. The first step, as I've written here, is just for the fixed step Monte Carlo method. For a variable step, or floating step Monte Carlo method, the first step can be omitted. Okay, let's start. This is the Laplace equation. You see the second side of the equation is 0. At the first step, we have to discretize the partial differential equation using, for example, finite difference concepts. Here, I've written the finite difference form of the second derivative of t with respect to x. As you see here, I have a grid here, or the mesh, the numerical mesh. I and j are indices of the points of the mesh, or the grid points. This is the point I and j. This is I plus 1 and j, the right point. The left one is I minus 1 and j. The upper one, I and j plus 1. The lower one, I and j minus 1. This is our fixed step Monte Carlo grid. The grid is facing in x and y directions are delta x and delta y. Not necessarily identical. You may have different mesh sizes in x and y directions. The other point here is that if you extend this equation to three-dimensional form, you can easily change the solution. So I've just written the two-dimensional form. The three-dimensional form of the equation just adds complexities, mathematical complexities, nothing more. Okay, this is the partial derivative in x direction. You can Similarly, write the partial derivative in the other direction, y, and then substitute these two finite differences into the main governing equation, and move the different terms in the equation, and transfer the partial differential equation into this framework. Or, as you see, the unknown function at the central point, I and j, is written on the left-hand side with the coefficient 1. You see the leading coefficient is 1. And the other points are written in the other side of the equation. This is our framework in Monte Carlo method. This is the right point t sub I plus 1j. This is the left node, this one, I minus 1 and j. This is the upper point and the lower point. The coefficients are p sub x plus, p sub x minus, p sub y plus, and p sub y minus in two-dimensional case. These coefficients are written here. It's so straightforward to derive these coefficients. Just substitute these finite difference in the equation. Px plus and p sub x minus are equal, and both of them equal 1 over delta x squared. And the denominator is twice 1 over delta x squared plus 1 over delta y squared. Similarly, p sub y plus and p sub y minus are this one. And the other point here is that if you substitute this expression, delta x equals delta y, I mean if you discretize this equation over a uniform grid with equal grid spacing in both directions, these coefficients simplify to 1 over 4 and 1 over 4, both of them equal. This means that all these coefficients are identical, equal to 1 over 4. It means that the temperature at the central point is the average of the temperature of the neighboring nodes. This is the well-known discretization of the Laplace equation in finite difference discretization. But here, you pay attention that these coefficients, the interpretation of these coefficients in Monte Carlo method is different from the interpretation of them in finite difference, for example, method. In finite difference, we say that the temperature of the central point is the average of the temperature of the neighboring point. But here, we say that these coefficients show the probability of the motion of the random walk from the central point to the neighboring points. For example, if p sub x plus is 0, this means that the random walk cannot move from the central point to the right point because the probability is 0. And also, if the probability is 1, for example, it means that the random walker has to go from the central point to the right point. Or if the coefficient of this, for example, term is greater than this one in non-uniform grid spacings, it means that the probability of traveling of the random walker from the central point, if this one is greater, to the horizontal neighboring point is greater than the motion of the walker to the vertical neighboring points. When we say that these coefficients are probabilities, it means that they have to obey the statistical rules. It means that the coefficients should be positive numbers, as you see they are positive numbers, and also they should be less than 1. Again, as you see, they are less than 1, all of them. And the sum of all probabilities should be 1. These are the fundamental rules of statistics. So, you can sum these coefficients. You can simply show that the sum of these coefficients is 1, not only in this case, but also in all other discretizations. Here I have written permutation of the Monte Carlo method for somehow complex equation. As you see here, this is similar to the Laplace equation, but we have a variable coefficients a as a function of x and y. Consider that the coefficient a should not be a function of t because the equation should be linear. So the coefficient is just a function of the independent variables x and y. If you want to extend the first step to this equation, for the sake of simplicity, I have just written the form of the results when we have identical grid spacings in both directions. So you can easily extend this result to the non-identical grid spacings. Here, a sub I and j means the value of the coefficient at the point I and j at the central point. You can easily prove these results. Again, as you see, they are all positive numbers and less than 1, and the sum of them is equal to 1. Okay, this is the first step of the Monte Carlo method with fixed steps. The second step is the initiation of the random walk. The random walk is a walker which moves between the grid points randomly. So you need some random numbers. So you start from the point you want. For example, I ask you to compute the temperature of this point. So you will start from this point, and randomly you can go to the to neighboring nodes in this grid. But if, for example, the value of the random number is between 0 and 1 over 4, you will go to the right node. If it is greater than 1 over 4 and less than 2 over 4, you will go to the right point, and so on. So based on the magnitude of the random number, you will decide to move or travel from the central point to the neighboring point. This is the random walk process. Generate random numbers, the rule of the game. This is a game. This is an interesting game. We are playing a game. The rule of the game is that you have to start from the nodes I and j, and if this is the interval of 0 and 1, we always generate random numbers in the range of 0 and 1. It's customary in all random number generators in Fortran or any other programming language. This coefficient here is p sub x plus. I have written p sub x plus here. The second one is p sub x plus p sub y plus. The third one is p sub x plus p sub y plus p sub x minus. As you know, the sum of all the four coefficients is 1. So the sum of 3 of them can be written or equals 1 minus p y minus. So if you write this expression, you have to perform 2 summations. But in this form, you just perform one subtraction. And the last one is 1, which equals the sum of 4 coefficients. So you have to compute the coefficients from the first step, okay, and then generate random numbers. If the random numbers fall in this interval, you have to move the random walker to the right point, because this is p sub x plus. The node ij goes to I plus 1j. If the random number falls in the second interval, you have to go to the upper node, the third interval to the left node, and the last interval to the I and j minus 1 to the lower node in the grid. This is the rule of the game of the motion of random walker, or the traveling of the random walker between the nodes in the grids, the Monte Carlo grids. Okay, there's one important point here, is that the order of these intervals should be descending. As you see here, descending order. You may pause the video and think about the reason. Why? The greatest coefficient, I mean that the greatest coefficient should be the first one. The reason is that, the Monte Carlo method, the most important problem of the Monte Carlo method is the computational time. So you have to minimize the number of comparisons in the numerical code. So if the greatest interval is the first one, the number of comparison or the number of if statements in the numerical code will be the minimum. Because the probability of falling the random number in this interval, which is the greatest one, is greater than the last one. So you don't need to compare the random number with the other one. So the number of if statements in the numerical code will be reduced. Okay, and the other point is that this random walk, there is another rule in this game. The first rule was about the process of traveling, or the rule of traveling between points, and the second rule is about the termination of the process. This random walk process, which starts from the first node that you want the temperature of that point, will finish when you reach a wall. I will explain about the meaning of wall, but for simply speaking, the wall here is a boundary which you have the value of your unknown function, for example, temperature here on that boundary. This is the wall in this context. So if you reach a grid point on a wall or a grid point with known temperature, you should finish the random walk process and start another random walk from the first point, and you have to repeat this random walk process for n times, and then at the end of each random walk you save wall temperature, so you have n wall temperatures. In order to compute the temperature of the point ij, you will very simply, sum the wall temperature that you have obtained at the end of n random walks. Sum them, I equals 1 to n. N is the number of the random walks started from the point you want, for example, ij, and ended at walls. This is the temperature of the wall during the random walk number I. And divide the sum of wall temperatures by n, which is the number of random walks. This is, you can easily compute the temperature of that point by performing n random walks and just saving the temperature at the end of that random. If you want the temperature of another point, you have to perform n other random walks starting from that point. This is the advantage of the Monte Carlo method. It means that in order to compute the temperature of a point, a particular point, you don't need the temperature of other points. Okay, in this part, let's consider a one-dimensional example of the Monte Carlo solution of a partial differential equation. This example is the one-dimensional form of the Laplace equation, or the second derivative of temperature, for example, is 0. This is not a partial differential equation anymore. This is an ODE, but I want to perform the Monte Carlo procedure as an example for this simple equation. We have 3 steps. The first step is to kind of discretize the equation. The next one is to perform the random walk. And the third step is to compute the temperature at your desired point. Okay, this is the governing equation. This example is based on the fixed step Monte Carlo method. So I need a grid point, and I need a grid or a computational or the Monte Carlo grid at the beginning of the solution. This is my grid points. As you see, the boundary condition at the left wall is 1, t equals 1, and the temperature on the left wall is 0. And again, the process is steady state, and the thickness of the wall is 1 unit. The solution of this differential equation is the linear distribution. It can be easily, it's very straightforward to obtain that. The blue line in the figure is the solution of the governing equation, which is a linear distribution. Exact solution is the linear distribution. For the sake of simplicity, I have selected 4 grid points. 2 of them are on walls with given temperatures, and 2 of them are inside the domain, or they are internal nodes. This is the first step, which is the discretization of the equation. I want you to compute the temperature of point 1. P1 means point 1, which is this one, the temperature of this point. The exact solution is 2 over 3, because this is the linear distribution starting from 0 and ending at t equals 1. So the temperature of this point is 2 over 3, or approximately 0.67. Okay, this was the first step. I can compare the accuracy of the Monte Carlo method with the exact solution. Okay, let's start the next step, which is the random walk process. I need to generate random numbers, and based on our rules, we will construct the random walk process. We had 2 important rules. The first rule was the process of traveling from one node to the other. Here, as you see, if the generated random number is less than 0.5, you have to go to the left. This is my convention. You can interchange these definitions. Go to the left point, and if the generated random number is greater than 0.5, you have to go to the right point. This is the rule, the first rule of the game. And the next rule is that if during the random walk process, if you reach a node on the wall with given temperature, you have to terminate the process and save the temperature of the wall. Okay, let's start the game. I have already generated, I guess, 17 random numbers, but I didn't write them on the board. And these are the result of the random walk process using those 17 random numbers. You can generate your own random numbers by hand, easily by hand, and play this game by yourself. The first, you have to start from the point which you need to compute the temperature of that point. So the point 1 is the first point node, or the starting points. As you see, all of these random blocks start from point 1. This is the advantage of the Monte Carlo method, is that you can compute the temperature of a point without paying attention to the temperature of other points. Okay, the first random number is greater than 0.5. So as you see, based on our rule, the random walker goes from point 1 to point 2. Point 1 to point to the right. So as you see, the random number is greater than, the first random number is greater than 0.5. So the walker goes from 1 to 2. The second random number is less than 0.5. So the walker returns back to point 1. Point 1 to 2, 2 to 1. And the third random number, again, is less than 0.5. So the walker goes from point 1 to 0, to left. And the point 0 is located on a wall with a given temperature. This is the end of the random walk process based on our second rule. And at this level, at this step, you have to save the magnitude of the temperature at the wall. So the temperature of this wall is 1. Save 1 in a parameter or in a symbol in computer, your computer code. Then start the second random walk. Again from the point 1. The fourth, 1, 2, 3, 4. The fourth generated random number is less than 0.5. So you have to go to the left neighboring node, which is again a wall. So the second random walk terminates here. And again you have to score or to save the magnitude of the temperature of the left wall, which is again 1. The next random walk again terminates at the left wall. So the third wall temperature is 1, but the fourth, pay attention to the fourth random walk. You have you go from point 1 to 2, and from 2 to 3, both random numbers in this random walk are greater than 0.5. So you have two successive motions to the right node point. So you reach the right wall with the temperature of 0. So the temperature of the wall at the end of the fourth random walk is 0. For example, pay attention to the fifth. You go from point 1 to 2, 2 to 1, again 1 to 2, and 2 to 3. And you reach the wall, the right wall with the 0 temperature. You may ask a question here: is it possible to create or to form a closed loop inside the domain? It means I go from point 1 to 2 and 2 to 1, 1 to 2, 2 to 1. It's not possible because the process of generation of random numbers is an ergodic process. Yeah, it means that you will definitely reach a wall during the random walk process. The fifth wall temperature is 0, sixth one is 0 again, seventh one is 1, eighth one is 1, and ninth one is 0. You can continue this process to 1 million random walk numbers, of course not by yourself, by means of a computer. The third step of the Monte Carlo method is to compute the temperature of the point P1 sub 1. As I explained in previous videos, the temperature of the point P1 is the sum of all walls, the temperature of walls at the end of all random walks, divided by the number of random walks. As you see, the number of random walks in this example is 9. So the denominator is 9, and the numerator is the sum of 0, 1, 1, 0, 0, 0, 1, 1, 1, which is 5. So the temperature, the estimated temperature of point P1, this point, is 5 over 9, which is approximately 0.56. Amazingly, compare the result of the Monte Carlo method with the exact solution, which is 0.67. You see, we are playing a simple game. I didn't use any extraordinary difficult mathematical knowledge. I've just played a game. I went from one point to the other, randomly, completely randomly, and I obtained a solution which is very close to the exact solution, as the relative error is 17%. Repeat this random walk process for 1 million times, for example, 100 times, 1,000 times. The result of the Monte Carlo method will converge to the exact solution, but the process of convergence is not monotone. It means that if you add some new random walks, the error may increase. But if the number of random walks goes to infinity, the result definitely will converge to the exact solution. In this section, I'm going to speak about the extension of the Monte Carlo method for the solution of parabolic partial differential equation, or the other title for this section may be the transient problems. It means that the Laplace equation, which contains the Laplacian of a quantity, is added to the partial derivative with respect to time. It's not important if you call this parameter time or anything else. It's just a mathematical symbol. Okay, so we have partial derivatives with respect to x, y, and z inside this operator, and also we have a first order derivative with respect to time or anything else. So with this equation is a parabolic equation, and because this equation contains the time derivative, it's called the transient problems in heat transfer or thermal sciences. Alpha is the coefficient of this relation, which may be thermal diffusibility in heat equation. If this equation is the heat equation, this coefficient is the thermal diffusibility. The process of the solution of the Monte Carlo method is completely similar to the previous examples. I mean, the Monte Carlo method consists of 3 steps. Step 1 for fixed step Monte Carlo method. The second step, or the random walk process, and also the third step, which is the computation of the temperature of the point. Okay, let's start the first step for the fixed step method. Again, we have a computational grid or computational mesh consisting of different nodal points shown by indices I and j. So you have, and in this step, you have to discretize the governing equation in fixed step methods using finite difference concepts, for example. So I have to discretize this new term in the equation. I want to discretize the partial derivative with respect to t using the backward finite difference. So the Laplacian term is discretized by the central scheme, and the time term, or the first term in the left-hand side of the equation, is discretized by the backward finite difference. It means that the partial derivative of t with respect to time is approximately equal to the difference of temperature at time n minus the temperature at time n minus 1, or the previous time step, divided by the time step size, delta t. So you can predict the temperature of the next step by means of the temperature at the previous time step. This is the only change of the discretization at the first step for the fixed step method. So after substitution of this new discretization in the equation, and also after substituting the central differences for the Laplacian term, and reordering the terms in the equation, and turning this discretized form into our desired framework for Monte Carlo method, we can obtain, or we can derive this equation here. As I told you, we need the temperature of the central point to be at the left-hand side with the leading coefficient equals unity, or 1. The other terms at the second-hand side show the coefficients show the probability of transferring or motion or traveling of the random walker from node ij to node I plus 1j, x plus, x minus I minus 1j, y plus I and j plus 1 at the upper node, and I and j minus 1 or the lower point. Then blue fonts here, the blue fonts in this relation are new terms, or the differences between the discretization of the transient heat equation or the Laplace equation, which was the steady state form of this equation without the partial derivative with respect to time. Pay attention to the blue symbols here. Also here we have a superscript n, which n in this parenthesis shows the time step. N means the nth time step. So this is the temperature of the central point, ij, at the nth time step. All other terms in the second side of the equation have the subscript n-1, as you see, n-1, n-1, n-n. So we can predict, using this equation, we can predict the temperature at the next time step by having or by computing the temperatures at the previous time step. This is the result of the backward discretization of the time term. And also, we have another new term here with the coefficient p sub 0. This is new, and because again we have this term. So, okay, excuse me, this one, we have this term here. This goes to the next hand side of the equation, and the coefficient of this term is is shown by p sub 0 at time n-1, and again at the central point. So P0 shows the probability of remaining at the present position. Because both subindices are INJ, so both of them show the temperature at the central point, or the point INJ, but this is at time n-1, then this one is at time n. So P0, which is the coefficient of this term, shows the probability of remaining the random walker at its current position. Other coefficients are defined similar to the previous case for the Laplace equation. If the mesh size or the difference or the distance between two nodes shown by delta x and delta y are equal, so we have identical grid spacing in both directions, you can easily compute the coefficients px plus minus, y plus minus, and also the fifth coefficient, which is new, shown by p sub 0. It's so straightforward to compute these coefficients. You can do it by yourself. Okay, so we have coefficients px plus 2, py minus. And these are the coefficients or the probability of the motion of the random walker to the right, left, upper, and lower grid points, of course in two-dimensional problem. And the fifth one, p sub 0, or the probability of remaining at the present position, is 1 minus alpha delta t over delta x squared. And you see again the probabilities are positive or non-negative, and all of them are should be less than 1. So this should be less than 1. And also the sum of all these probabilities equals 1. Consider we have a coefficient here at the denominator 4, and we have 4 coefficient. So you have to multiply this relation by 4 to compute the sum of for these 4 coefficients. So the first step is completed, which was the discretization of the governing equation over a fixed step mesh points, and computing the probabilities of traveling to the neighboring points or remaining at the current position. The next step is to perform the random walk solution, but this time for a transient problem. Consider that we have two differences with respect to the steady-state problem or with respect to the partial differential equation without this term, this first-order derivative. Similar to the previous case, we have to start the random walk process from the position ij, which is given to you, and you have to compute the temperature at this point. So this is the initial position of the random walker, similar to the previous case. But this time, we have another given parameter, which is time. So you have to compute the temperature of a point at a specific time. So the random walker starts from position or the point I and j and at time t, and you will travel back in time until you reach the initial condition at t equals 0, for example. So the random walk process in transient problems starts from a specific time, for example t equals 10 seconds, and at a specific point, for example here, and you will go back, travel back in time until you reach the initial time step. Start the random walk from point I and j and time t, and step back in time. This is the first difference of the random walk process in transient and steady state problems. Okay, if needed, you may compute t at other points and other times. So the advantage of the Monte Carlo method is that you can compute the temperature of a point at a time without needing to compute the temperature at other times and other points. So, but if you want to compute the temperature at another time, you have to repeat this time-consuming procedure for other times and other points. This needs a huge computational time, and this is the disadvantage of the Monte Carlo method. But the advantage is that you can independently compute the temperature of a point at a time without paying attention to other times and other points. Okay, if needed, you may compute temperature at other points and the times by repeating the random walk process again from 0 from another time for another time or another point. You need a time step. So since you want to go back in time, similar to the case that you need to discretize the space to using grid points. In this case, you need a time step. It means that you have to discretize the time as well. So you need a time step size. So t equals m0 times delta t. So for example, if the time step is 1 second and you want to compute the temperature at time equals 10 seconds, so you have to step back in time in 10 levels because the total time is 10 times the time step size. M sub 0 is the number of steps you need to go back in time to reach the initial time. The random walk, the second difference between the steady state solution or the Laplace equation and the heat equation or the transient solution is the condition under which you can terminate the random walk process. In steady state cases, I said that when you reach an absorbing wall or a wall with a given temperature, you can terminate the process and save the temperature of the wall. But in this case, you are traveling back in time. And it may happen that when you are traveling back until you reach the initial time, or t equals 0, for instance, it may happen that during this traveling back in time, you may never reach the wall. And when the time steps, the number of time step, I mean m sub 0, finishes, you may be in one of internal nodes at the initial time. You may be in one of internal nodes inside the domain. It means that when you are computing a transient problem, you need an initial temperature or initial distribution of temperature at t equals 0. So if the random walk terminates at wall, you save the temperature of the wall. If the process of the random walk never reaches a wall or never touches the wall, and the process terminates when you are in one of internal nodes, you have to save the initial temperature at that point. Because the initial temperature may be a function of x and y. So if you terminate the process at a point, you have to save the temperature of that point, initial temperature of that point. So the random walk terminates when you reach a wall, or this is new in the transient problem, or when t equals t0, or usually 0, t0 is 0. T sub 0 equals 0. After m sub 0 steps, m sub 0 is defined here, is the number of steps you need to travel back in time until you reach the initial time. If you reach a wall, then you have to save the temperature of the wall. Okay. If you don't reach a wall during this random walk process until you reach the initial time, you have to save the initial temperature t sub 0 as a function of x and y based on the location of the walker at the initial time. T sub 0 is a function of x and y. So again, the process is very simple, but I presented just some modifications. If you write a numerical code, or using Fortran or C++ for the Monte Carlo method, for the Laplace equation, you can easily extend it by minor modifications to solve the transient problem or the parabolic partial differential equation. This is the second step of the Monte Carlo method. And the third step is again similar to the previous one, completely similar. The temperature at point x and y and at time t equals the sum of n is the number of random walks started from the point I and j and terminated at walls or at the internal nodes. Is the sum of temperatures of walls or the initial temperature during n random walks. So you can easily add the temperatures of the walls and the temperature of the random walker at the initial time, and then divide this summation by the number of random walks, and the result is the temperature of that point at that time. I will explain the modifications of the Monte Carlo method for the source term. If we have a source term here in the equation. So the source term handling in transient Monte Carlo method is completely similar to the steady-state case. So the source term is treated completely like a steady-state case. There is nothing new about the source term in transient solution. And in the variable step method, the difference is that you don't need to discretize the equation. This is a limitation of this fixed step method. But in variable step method, the time step size, delta t, is variable. The temporal step size, or delta t, is also a variable quantity. So in variable step method, delta t, or the step size, is a variable quantity and should be computed based on delta r. Delta is the spatial step size in polar coordinate or in a spherical coordinate, and the delta t is the time step size, which is a function of the spatial step size. For more information about the details of the variable step method in transient problems, you can read the chapter 8 of the numerical heat transfer handbook, second edition. Chapter 8 contains many important details about the extension of the transient process, the transient equation, transient Monte Carlo method for the variable step methods for curved boundaries, especially when the geometry contains curved boundaries. In this section, I want to introduce the extended version of the Monte Carlo method for the solution of the Poisson equation, which is the non-homogeneous form of the Laplace equation. The type of the equation is again an elliptic. Poisson equation is an elliptic equation, partial differential equation, but this time we have a function in the second-hand side of the equation, which is the source term of the equation, or in thermal sciences we call discernible volumetric heat generation inside the material. Okay, so we have this is called the Poisson equation when the Laplacian of a quantity equals a non-zero function. The equation is called the Poisson equation. The process of numerical solution of this equation using the Monte Carlo method again consists of three steps. The first step is the discretization of the equation. The second one is the random walk process, which is completely similar to the random walk in the Laplace equation or the homogeneous version of the equation. And the third step, which contains some new features. As you see, we have two differences. The first one is in discretization, so this term is new in comparison to the Laplace equation. And again, in computing the temperature at the last step, we have a new term here written in blue font. Okay, so the first step is straightforward. You substitute the finite difference approximation of the temperature derivatives in this equation and try to turn it to the desired framework. Again, the temperature of the central point with the leading coefficient 1, you see here, and the other temperatures of the neighboring points. With here we have 4 coefficients: px plus, px minus, y plus, y minus, and this is the source term of the equation, which can easily be obtained. Okay. The next step is, as I told you, completely similar to the random walk process for the Laplace equation. And pay attention to the last step. As I told you, the random walk process will terminate when you reach a wall with a given temperature. So, and at the last step, now you have to add the temperature of the walls that you have reached during the random walk process. So this term is completely similar to the previous case, and divided by the number of n is the number of random walks, n is the counter of the random walks, and T sub W is the temperature of the wall, and nothing else here. Plus, this term is related to the source term of the equation. We have delta x delta y over 2k. Chi is the conductivity of the material here, as you see, and it's a coefficient of the equation. And this is this coefficient completely appears here. They are constant values. Similar to the previous case, we have a coefficient 1 over n because we want to compute the average of, in this case, wall temperatures. In this case, I will explain what these summations are. Okay, this expression is the coefficient of the source term. 1 over n is shows the average of this expression for n random walks. And the first summation, again, is similar to this summation. N is the counter of the random walks, the first random walk to the nth random walk. But the second summation, shown by the counter k is the new counter here. K shows the number of steps during a single random walk. So, when you are performing the random walk process, you are going from one nodal point to the other point. This is k equal to 1. The next transfer from the next nodal point to the third nodal point, it corresponds to k equal to 2, and so on. So this summation starts from the first random walk from node ij to the neighboring points, randomly, of course. And Mn shows the total number of random walk steps during the random walk. Number n starts from 1 to n, or n varies from 1 to n. For each of these n random walks, we have n number of steps. Okay, so you have to compute the magnitude of the source term g for the nth random walk, and for each motion from one point to the other point, and divide the result by n, and multiply the result by this coefficient, and then add this result to this one, so you can compute the temperature of the point I and j. This means that at the previous version of the Monte Carlo method for the Laplace equation, you just needed the value of the wall temperature at the end of the random walk process. You had nothing to do with the process between the initial point and the last point. It's not important for me what happens during the random walk. You can promptly reach the wall at the second random walk generation, or you can create a loop inside the domain, and then after 100 random walks you reach the wall. The important part of the random walk process in previous version was the temperature of the wall at the last random walk step. But as you see in non-homogeneous for partial differential equations, you have to pay attention to what happens during the random walk process from the first node to the last node when you reach the wall. This summation, the second summation here, shows what happens during the random walk process number n. From cut equals 1, this is the first step in the random walk, and this is the last random walk. So if the distribution of the source term inside the domain is a constant function, or the source term is distributed uniformly, or the value of the source term at different point is identical, you can simplify this equation. So t sub ij equal this is completely similar to this one. The first term in the right hand side has nothing to do with this source term. But the second one, as you see, g is written here. It means that g is not dependent, is not a function of different coordinate points or positions. So you can eliminate the second summation, and if the function inside the summation is 1, it means that you have to count from 1 to n, or to add n number of ones. So the result is n. So you can write g here, because g is a constant, similar to delta x, similar to delta y, or other properties. And also write 1 over n here, because this shows a kind of averaging, and also the first summation. But the second summation simplifies to a sum of n number of ones, which is equals to mn. We need to compute gij. It means the value of the source term at different points during the random walk, and count the number of steps. You need to count the number of steps during each random walk process, which is shown by M. Right, in this section I am going to speak about the different boundary conditions in the Monte Carlo method, and how to handle such boundary conditions in different applications. Okay, so the boundary conditions. The governing equation is the Laplace equation, or the Poisson equation, or the heat equation with the source term. We have, generally speaking, we have 3 types of boundary conditions in different physical or mathematical applications. The first type of boundary condition is the absorbing boundary condition, or in mathematical framework, the Dirichlet, or the first type boundary condition. In this type, you I give you the magnitude of the unknown parameter, such as temperature here, on the boundary. So T is constant. This is the other name of this type. The first type is the absorbing boundary condition. the title shows that the random walker which strikes the first type boundary is absorbed by the boundary. So we call it the absorbing boundary condition, and the process of the random walk process will terminate when the random walker strikes this type of boundary. The other one is the second type is the reflecting boundary condition, or the Newman type boundary. In this category, we have to give you the magnitude of the derivative of the unknown parameter on the boundary. So Q here is the heat flux, which based on the Fourier's law is minus K, conductivity, partial derivative of temperature with respect to the normal direction of the wall is constant. Because K is a constant, means that in this type we have the derivative of the temperature is none. The other name based on the Monte Carlo concept is the reflecting boundary condition, because the random walker which reaches the wall will reflect back or bounce back again towards the internal nodes. So the name or the title of the second category is the reflecting boundary condition. And the third one, which is partially reflecting boundary condition, or the rubbing type, or the third type boundary condition. As you see in this category, you will have a combination of the temperature itself and its derivative on the wall. Here, this is the heat flux, and this is the Newton's cooling law. This is the conservation of energy on the wall. So as you see here, we have K, H, and T sub infinity, and all of them are known parameters, and this equality constructs a relation between the magnitude of temperature and its derivative on the wall. So this is the partially reflecting boundary, or the rubbing type. But this was a brief introduction to three types of boundary conditions. For example, consider that this wavy line here is the wall or the boundary of the domain, and the boundary is the reflecting boundary. Or for example, if Q equals 0, it means that the wall is adiabatic or isolated. So this is, as you see, the derivative of temperature with respect to x. X is the normal direction to wall. So in this example, it's horizontal. And the derivative is 0, it means that this is an isolated wall or adiabatic wall. And again, we have our grid points. The central node here is located on the wall. And the right node I plus 1j, the left node I minus 1j, and upper and under lower walls. As you see, this section is contributed to the fixed step Monte Carlo method. In variable step Monte Carlo method, the step changes, and we should present some other modifications to this method to encounter different types of boundary conditions. Okay, so we have a fixed step grid points, and the central point is located on an adiabatic wall. In such cases, this is an example. You have to discretize the boundary condition. As you know, at the first step of the fixed step Monte Carlo method, we have to discretize the governing equation. Here you have to discretize the boundary conditions as well. Here the boundary condition is this relation, the derivative is 0, so you have to discretize it using the central difference concept. It results that the temperature of the right node should be equal to the temperature of the left neighboring node, these 2 points. But as you see, we don't have this point in real physical system, because this is the wall, and this is our material. So the I plus 1j is the virtual node, or the ghost node, which will be eliminated in our future relations. Okay, and then substitute this relation into the discretized form of the governing equation, and omit the temperature of the ghost node, which is Ti sub I plus j. And you will obtain a new governing equation which only 3 temperatures of the upper, the lower, and the left node in our case, just these temperatures exist in the governing equation, and then you can continue the random walk process. But when you reach this node on the wall, you will continue the process with a new relation just for this node. So this is a reflecting boundary condition, because the random walker which hits this wall will come back, will go back through in the internal nodes, but just for the process at the wall, you have to use a new or another modified form of the discretized equation. So I said that P is the probability of motion of the random walker from node ij to node I plus j. The coefficient is 0, so the probability is 0. But the probability of P sub x minus changes in comparison to the probability for internal nodes. A coefficient here appears, a factor 2. So Px minus is twice Px minus for internal nodes. The next step here was to perform the random walk process. As you know, in the Monte Carlo method, the first step is to discretize the governing equation. Here you have to discretize the boundary conditions as well. The second step of the Monte Carlo method is to perform the random walk process. Okay, then you can perform the random walk process using the fixed step method as before. But in some complex applications, such as the systems involving curved boundaries, you may choose another version of the random walk process, which is called the floating point random walk or the variable step random walk process. I will briefly introduce the floating random walk process here, and for more details about this type of random walk process, you can read chapter 8 of the numerical heat transfer handbook, chapter 8, which is devoted to the different Monte Carlo methods for the heat equation or heat transfer problems. In that reference, chapter 8, these floating random walk process has been explained in more details. Okay, as you see, this is our geometry. This is the left wall. This one is the right wall. And we are going to compute the temperature of this one. This is the initial starting point of the random walk process. But this time, I don't have a grid. I don't have a grid network. I don't have grid spacing or anything else. So I want to perform the random walk process using two-dimensional polar coordinates. In this part, I just explained the two-dimensional case. You can easily extend my explanations to three-dimensional cases using spherical coordinates. So here is the initial point. I want to compute the temperature of that point. So I start my random walk process from that point. The coordinates are x sub I and y sub I. And in this case, I want to proceed the random walk process by generating a random walk process based on the polar coordinates. So at the first step, I have to compute the shortest distance between this point and boundaries. For instance, the shortest boundary or the nearest, the shortest distance or the nearest boundary is the left wall. So this is the variable Ri, which is the shortest distance between the new point or the random walk point and the nearest boundary. This should be computed using a computer algorithm to find the distance between the point and the nearest boundary. And this is called R sub I. Then draw a circle. The center is the point, and the radius is computed. So then you can transfer from or move from the center of the circle to any of the points located on the surface of the circle based on the random number generation. So you have to generate a random number and then multiply it by 2 pi, twice pi, because all random numbers are between 0 and 1, and the angles along a circle vary between 0 and 2 pi. So then multiply it by this factor and find the random number which specifies the next location of the random walker at the next step. For instance, here is the origin of the angle phi. So approximately 20 degrees, I think. This is phi, which has been computed completely randomly. And then move the random walker from here to this point. This is the circle, and this is the random number. This is the next position of the random walker at the next step. Then repeat this process again. And you have to compute the shortest distance between this point and the boundaries, the nearest boundary, which in this case may be the right wall. So in here is the blue circle. This is the R sub I, and then again generate a random number and define the third position of the random walker. For example, is here. Then again compute the distance between the point and the wall and go on. This is the process of the random walk process in two-dimensional case. Using the polar coordinate relations x sub I plus 1, or the x position of the random walker at the next step, equals the previous position plus Ri. I've explained the definition of Ri, cosine phi. Phi is a random number, but Ri should be computed based on the geometrical details. And similarly, the vertical, the position of the random walker at the next step, and so on. For the spherical coordinates, the main algorithm is similar, but these definitions should be modified for the spherical, based on the spherical coordinates. Now, this is the second step of the random walk process, but this time using the floating random walk process. Other details are similar to the fixed step random walk. And the final step, or the third step of the the Monte Carlo method, is to compute the temperature of the point, or the initial point, based on the wall temperatures obtained at the end of n random walk process, starting from that point. So the temperature of the initial point, which was x sub 0 and y sub 0, equals 1 over n. This is the summation from n equals 1 for the first random walk to the nth random walk process. T sub w is the temperature of the wall at the end of the random walk processes, and n shows the counter of the random walks. This is the average of temperatures of the walls at the end of random process. Encounter the source term in the equation. Here you have to add another term to this temperature and to compute the effect of source term Q in the equation during the random walk process. Again, plus 1 over n. The first summation is over the random walks, starts from 1, ends at n, and the other summation shows the process of traveling during each random walk process. L shows is a counter of the random swapped steps during each random walk process. L from 1 to m, n, and n is the number of steps for the nth random walk process. Q is the source term of the equation. R sub n and L shows the shortest distance between the point and the boundary, as you know, raised to, and the denominator is S shows the dimension of the equation for two-dimensional and three-dimensional equation. This parameter equals 2 and 3 respectively, and K is the coefficient here. Is the coefficient of equation, or the thermal conductivity in heat transfer. So this step is for both for two-dimensional and three-dimensional cases. You have to just change this constant at the denominator 2 or 3 for two-dimensional or three-dimensional cases. But this step is just for two-dimensional. For three-dimensional cases, you have to change these relations based on the spherical coordinates. And also in three-dimensional cases, you have to generate two random numbers for two spatial angles, phi and theta. But in two-dimensional cases, you can determine the next position of the random walker by just generating one random number. And as I told you, this process is very helpful in handling the curved boundaries. There are some kinds of important remarks or future works or concluding remarks in this section. These points will give you enough motivation to continue this path towards obtaining more complex Monte Carlo methods. For example, in these videos, I just explained the solution of the heat equation, the elliptic or the parabolic heat equation, but it's very interesting for us to extend the Monte Carlo method for the solution of the Navier-Stokes equation, which is the governing equation of the motion of the fluids. Now, this is the energy equation or the heat equation written for a moving media or for a fluid. As you see here, we have the material derivative, and in this derivative you have a velocity component which can be computed from the solution of the Navier-Stokes equation. The general algorithm is similar, but you have to discretize this equation. You see these two terms in the first side of the equation are similar to the heat equation, but this term is new. And then after the discretization process, you have again the coefficients of the neighboring particles and also the probability of remaining the random walk at its current position. Then you can continue. So the difference between the Monte Carlo method for the energy equation for a fluid and for a solid body is the different probability coefficients. In the final discretized equation, you can discretize the terms inside, the advective terms inside the material derivative using the 4-bar difference. Okay, the next point is the anisotropic form of the anisotropic means that the material, the different properties of the material is direction dependent. So when you are performing the random walk process, as you see here, the random walker is located at the center at point t, for example, and then it's going to find its way to the neighboring particles. So in our previous case, the random walker can go to the right, to the left, to the upper, and to the lower neighboring nodal points. But here, as you see, there is a fifth choice for the random walker to go, for example, to the upper right node. As you see, the direction of motion of the random walker is dependent to the material property, or the motion of the random walker is direction dependent. So this material is kind of anisotropic. So during the random walk process, you have to choose 5, for this case, of course, 5 intervals between 0 and 1. And as I explained before, based on the magnitude of the random walk, you may go to 5 directions. This is an example of them. For example, one anisotropic material may contain the direction dependence like this. So the property of the material is in a way that the random walker may go to the left and the upper node here. Okay, and no difference. So you can easily change your numerical code to consider the solution of PDEs for anisotropic materials. Okay, and the other point or the other challenge is the solution of the hyperbolic type equations. like the wave equation, the hyperbolic type equations have a special behavior in their solutions, like the jumps or discontinuities, such as the shock wave in fluid mechanics, and also the behavior of the hyperbolic equation or the microscopic nature of hyperbolic equation is not random. So our described random walk process is not appropriate for the solution of such equations. There are some modifications of the random walk process for the Monte Carlo methods for the solution of the hyperbolic type equations to handle sharp discontinuities or jumps in properties. And the other challenge is the solution of the nonlinear problems. In previous videos, I've emphasized on the linearity of the governing equation. So I told you that the coefficients should not be a function of the dependent variable. But if the problem is nonlinear, there are many active research fields for the solution of the nonlinear problem. As you know, the world is nonlinear. And the hybrid Monte Carlo method, the Monte Carlo method can be used in a hybrid manner with other deterministic, for example, numerical methods. And this is again to have the advantages of both deterministic and stochastic numerical methods. And there are some other branches or permutations of the Monte Carlo method. For example, the Monte Carlo based on the Green's function, or based on the walk on a sphere process, or the Monte Carlo method after rewriting the PDE as an integral equation. So you first convert the partial differential equation to its equivalent integral form, and then use the Monte Carlo method.